The other way is, taking a step forward, and this is what I will run through now with everyone using R in a couple of minutes, is Suryawanshi et al. In 2012 sort of took a step forward from Fawcett and Hickling back in 1997, and kept the field method very, very similar, but at the same time sort of added a layer of robustness to their calculations. And I will just run you through what they have done. Again, principally, the equation to arrive at our population estimate says the same. N hat equals to G hat times mu hat. The only difference between Suryawanshi et al. And Forces and Hickling is how we estimate the G hat and the mu hat, right? Which is what I'm going to just explain in a bit. And again, it might sound very, very complicated, but I always encourage people to sort of think and have a functional understanding of things, even if it's not completely, if you don't get the math completely. So let's not get too bothered by that. So we can build our understanding slowly. Basically, what we use is, the BB recapture package in R. BB, like the BBR here, really stands for Bayesian Behavioral Recaptures. So we're basically using a Bayesian approach to model some of these things. We're actually using Bayesian approach to model number of groups. Very, very simply, what Bayesian does is it sort of says, okay, we're going to have a prior distribution and a likelihood of that prior distribution. The multiplication of the two will be my posterior distribution, or in other words, the distribution I want. So that's what we're going to use for group sizes, and I'll just walk you through what we do. So basically, to arrive at G hat, we use a two-survey mark recapture methodology. And we model the detection for the two observers separately. So for observer 1, it's separate, and for observer 2, it's separate. And what we're fitting is the MT model. So if you go back in time to read some of the really good work by Otis, I think it's from 1978, and I hope I've got the year correct. If not, I'll just check and update it. If you're looking at detection probability for mark recapture surveys, Otis suggests that there can be 3 different types of models. There is the M0 model, which I think, if I'm not mistaken, that says, the detection between observer 1 and observer 2, or the mark and the recapture, is the same, right? There's no change. MT model, which we're using, says that actually there is a difference between the two surveys or the two observers. And we spoke about this in the first class, right? By the fact that you're changing the time between the two observers will potentially result in different captures and recaptures, and that is what the strength of the method is. So that's what the MT model is. And last week, if you guys remember, we had a chat about, but observer 2 might see less than observer 1 because, there's evasive movement of ungulates, which is a very valid point. So there, one can use the MB model, which we don't use, but, one can use. And what the MB model says is that there is a behavioral impact on the second observer compared to the first observer. And there can be 2 types of impacts on the second observer. One can be a reduced detection, because of observer 1, let's say observer 2 doesn't detect as many ungulates because the ungulates are running away. Or the observer 2 can have an increased detection because, because of observer 1, for whatever reason, the ungulates tend to stay where they are. So my point being, without getting bogged down into too many details, we can account for some of these ecologically and natural history-wise relevant factors in the field using these models. But for our purpose, we'll use the MT model, which basically says, there's a variation between the 2 surveys. We will use uninformed uniform priors. Remember I talked about, how in Bayesian statistics you have a prior distribution and a likelihood distribution. And the reason why we use uninformed uniform priors is because I'm assuming we're doing whatever this survey is for the first time. So, the group sizes that we get will be for the first time in that area. If you were doing, let's say, long-term studies, you could have uniformed, informed uniform priors, because you would know maybe if the group sizes are similar across time. And then we do about 10,000 MCMC with burden of about 1,000, and I'll explain what that is in a second. And basically, the model output gives us two detection probabilities by the MT model for occasion 1 and occasion 2. Just look back here, as I said, we do two different, we model the detection for the two observers separately. And and then we take the detection probability of occasion 1 as the detection probability for the first observer, and we take the detection probability of occasion 2 as the detection probability of the second observer. So just, I completely understand this is a lot, but let me just show you what this means. So what is going to happen is, using whatever I just said in the previous slide, when we run the model, we will have an output for G0 or group sizes, which is something like this. So as I said, we're going to input our own group sizes as the sort of prior distribution. And because, it's the first time we're doing it and we're using uninformed uniform priors, the likelihood is similar for those group sizes to be, and then the output looks something like this. If there's a question in the chat. Okay, sorry, Chloe has a question. I'm just going to read that out. Yes, and guys, please feel free to put in questions. So Chloe asks, what about weekly informative priors? Would that risk to influence the type of data that you usually have with these surveys? So Chloe, that's a great question. So the 2 points. So my grip on Bayesian statistics is not the best. I mean, it's quite functional. So what I have realized over time is, if it's the first survey you're doing, especially because group sizes is a very variable sort of factor, even with similar species. So for instance, we've had you guys might recall from the last class, where we spoke about Uriel, two populations very close to each other, very different group sizes. And we've seen this with other species as well. So what you define as weakly informative also can be very, very influential in the output, especially if you have very limited number of groups. If you have a lot of groups, then it might taper out. So I'm always more comfortable in using the data the way it is, and sort of going with uninformed priors if it's the first time, and then sort of using weakly informed priors for the next steps. But yeah, I'm sure maybe there's a better answer out there, and I can find that. Is that useful? I just want to see if that's what you meant, or if you want to speak up. Okay, perfect, cool, great. And yes, guys, please feel free to stop me, and yeah, also feel free to not type and just speak up. So anyway, so what the output will look like is something like this. On the x-axis, there's going to be a range of estimated number of groups, and on the y-axis, there's going to be a procedure probability. So this is an actual data set from a study that we published this year in Oryx, and I can share the paper with you guys. Already what you can see is the probability of the group size being, must be around, let's say, 20 or so. I'm just taking a guess, is really, really high, and it significantly tapers after that. So, already there's a more informed group size distribution that we can sort of look at. So that's about group size. What do we do to the mean group size? So if you take a step back to Fawcett and Hickling, as I said, there the mean is a simple arithmetic mean, but what Suryawanshi et al. Proposes is a step forward and a bit more robust way to calculate it. What we do is, again, using our own data, we generate a distribution of estimated group sizes by bootstrapping our own data set 10,000 times with replacement. In other words, what we do is, let's say if you have 30 groups of varying group sizes, we will tell, let's say, why don't you go into those 30 groups 10,000 times? Think of those 30 groups in a hat, as 30 numbers being the group sizes. And you go in, you remove one, and you do that 10,000 times. And each time you remove it, you put it back into the hat. And you're going to get a data set that is 10,000 sample size big rather than just 30. So what it's going to do is going to give you a distribution, something like this. Of those 10,000 times that you have sort of gone into that hat and removed group sizes and put it back in. And what this distribution really has is on the x-axis, we will have the estimated mean group size, and on the y-axis, the frequency. In other words, how many times was that mean group size obtained, once we did that, picking from the hat and putting it back into the hat. So as you can see, theoretically, it's very similar to estimated, just an arithmetic mean calculation, but it's a bit more robust in terms of its in terms of the whole using your own data set. So as you can see from here, that would be the distribution, and if you take the mean of that distribution, in this case for our data set, the mean was 15 individuals, we can use that. Now taking the last step, how to combine the G hat and the mu, as I just sort of theoretically showed you guys. This is what we basically do. This is the first graph I showed you of the number of groups. The second graph I showed you of the estimated mean group size. And then we will combine these two, A and B, to get a distribution of estimated population. In this case, it was Nilgiri thar, which is a species of caprine found in southern India. It's interesting, it's one of the few species that's of caprine that is tropical. And then we get a population estimate and its confidence interval. So I'll just explain how we do that. So what we basically do is we generate a distribution of n estimate, which is n hat, which is this distribution that I spoke about. How do we do that? We multiply 10,000 random draws of G hat weighted by its posterior distribution. So what we tell R is, why don't you go into this distribution, right, and remove 10,000 group sizes, number of groups, weighted by the posterior distribution. As you can already see, if just logically, what that would mean is that there is very much a likelihood of this group size coming out more. But there will be some likelihood of these group sizes coming out as well, and some likelihood of these group sizes coming out as well. And then we multiply that by the posterior distribution, and we multiply that by drawing means of group sizes from here. So rather than getting one value, what we get is sort of this frequency distribution of estimated population of our species of interest. As you can see, for us, we have this sort of distribution that sort of told us, we can have around 200 individuals to maybe even 1,000 individuals. And that's obviously not that helpful. So what you then do is you say, okay, the median of this distribution, and I can explain why median in a bit, is going to be my estimated population. And the confidence intervals are the 2.5 and the 97.5 percentiles as the 95% confidence intervals. So essentially then I get an output that says, my estimate is around 500 and whatever that is, lower bound is about 350 or so, and upper bound is about 820 or so. So that's really that's really the theory behind all of this. And I will just recollect to us our sort of the data that I just spoke about. Because in a minute, I will switch my screen from presentation to R and show you how we actually analyze it. So let's just recall the data. This is exactly the data I showed you 4 or 5 slides ago. Again, it's the data from India. It's for blue sheep. There are these group sizes, different group sizes. There are these capture recaptures. Again, just to quickly recall, There's 11 groups in total, 7 recaptures, observer 1 captures, 3 unique groups, observer 2 captures, 1 unique group. While I analyze this, I will also run it for this data set. It's the same as the previous. The only difference in this data set is what I've done manually, just to show you how things will affect different things, is again, it's 11 group sizes, same area, same species. I have changed the number of recaptures. In other words, the 2 data points that were recaptured, I have made them solely observer 2's captures. So in this data set, there are lower recaptures and more single captures. So I'm just going to go and analyze this and sort of show you guys how that's done. So if you just bear with me, I will just switch my screen to my R. Just give me a second. Great. Can you guys see my screen? If people can see, just gonna see in chat. Yeah, perfect. Super. So this is how super. Thanks, guys. Yes. So this is, sorry, firstly, my R is very cluttered, but if you can just see here, I'm just gonna make this bigger for you guys so we can all sort of see. So let's, if you guys can see up here, just here. So, and I will share these codes with everyone, right? So this is more to really understand what the code is doing, and then in your own time you can run it on your own data, and then you can see how things are. So we basically need 2 libraries in R, and I apologize for people who don't use R that much, but we can talk more about how to get everyone started, maybe over email or whatever. But this is assuming people have some functional sort of understanding of R. So the 2 libraries we will use, the 2 packages, are the BB recapture package and the HMISC package. BB recapture is the the Bayesian behavioral recapture, and this package really helps. The HMISC package is more for understanding confidence intervals. So what we basically do is we have to write a function that we've written here, and some of these parameters you can read in the BB recapture package. But essentially, there is a data set which I call DOS. There is a number of bootstraps that I just spoke to you about before, and we're going to say 10,000. And just for the model to work, we have to give it a maximum population, and you just give it quite a high population. So like even if your data minimum count is 200 or something, and even if you write the maximum population is 5,000-6,000, for instance, it should work. It just has to be quite higher than what your actual maximum would be. So that's what this first line is doing. Really, it's quite simple. Then the main part, this part, is the part about the group number of groups. The whole Bayesian part where I spoke about the prior and all of that. So what you're basically telling R is that you're running the BB recap function on a data set. This 2 to 3 is the columns of the detection and non-detection of the groups. You're telling it, I want to use the MT model, right? And as I said here, you can also use the MB or the MO, so you can see how things might change if you tell the model, okay, in my study site, we had a behavioral impact. So there's a question in the chat, I think. Can you share the code? Yes, definitely. So I will share the code both as a .r file and a text file, absolutely. In fact, it's all up on GitHub already. So I can also share the Git repository code with everyone. But I wanted to just run through it, knowing that, yes, it's going to be a little heavy to sort of just listen to somebody and know how the code works. But I think it's a bit nice to just sort of see it once for what it is. But yeah, absolutely, I will share the codes. And what I would recommend is people to make dummy data sets, or I can provide some data sets that we have to just run the code to familiarize yourself with it. So yes, you tell it, okay, the model is empty, uniform prior, as we said. This can be changed, as we also said. The output, you just have to say, it's a complete output. There's other differences that you can look into, but not too important, and you just have to give it a max nibble. You just have to give it as the maximum population. So that's sort of the limit of the model. So that's what the group size bit is. Sorry, the number of groups. I keep messing that up. So that's for the number of groups. And this whole section here, and I won't get too much into it. Mostly what this is really doing is it's, as you can see with the hashtag here, it's creating that graph B, the distribution of mean group sizes. All it's doing is going into your data set, of the group sizes and saying, I will bootstrap it 10,000 times and get a mean estimate. And then I get a distribution. And then this is the lower bound and the upper bound, for the eventual, from the eventual distribution. So I will just run this function. So if you just run it from here, it should run all the way through, right? And once you set your working directory and once you import your data. So I'm going to import the first data first, the one where we had 11 groups, 7 recaptures, and I think group observer 1 had like 3 unique captures and observer 2 had just 1 capture, right? So I'm going to call it that, as you can see here, and I have named it dos.csv. If I run that, I have my data. We can have a look at the data again, just to convince everybody that that's what we're using. See, study areas Himya, those 4 blocks, and these were the sort of observation 1, observation 2, and there's some additional data that I had. Who was the observer? What was the classification? We're not bothered about that for now, right? And this is the code we have to run. As you can see up here, as I said, the main function is the data, the number of groups, and the max population with this function. And that's exactly what we're going to do here. dos.bay is the name of the function, as you can see here. And 6 to 8 is basically column 6, which is column group size is column 6. As you can see, 1, 2, 3, 4, 5, and 6. 7 is the captures for observer 1. 8 is the captures for observer 2. I'm running this with 1,000 number of boots. You can run it with 10,000. And I've just given it a label of 3,000, right? And if I run that and I wait, so it's run, and if I just call that in R, we get the following output. And I can walk you through this. The first here, and it's written up here actually, see output right here. So this is what the output really is. The first is the N estimate, right? The second is the number of groups. The third is the mean group size. Fourth, as you can see, it's the lower confidence interval. Fifth, here is the upper confidence interval. And the second last number here is the detection probability for observer 1. And this is detection probability for observer 2, right? So this is quite straightforward to understand. So in other words, in this population of Hemia, of blue sheep, we estimated about 171 blue sheep. I mean, you would obviously round it off because we cannot have 0.727273 blue sheep. So there's 171 blue sheep, lower bound of 157, upper bound of 229. Detection probability of observer 1 was about 0.79, of observer 2 was 0.64. And yeah, mean group size is about 14.2 individuals per group and 12 groups. Now, just quickly, I will call in the other CSV, DOS2, I've called it. And if you recall from my presentation, the only difference between DOS1 or DOS and DOS2 is there was right here. There's less recaptures, right? There's a question in the chat, I think. Yes, Helena, I think that's the repository, yes. But I will just let me update it quickly right after this, because the code that I'm showing you guys is a bit better than the code that was there. We've just fiddled around with a bit of the bit better. That's the that's the Git repository. Super. So yeah, the only difference between the two, the group sizes are all the same, and there's less recaptures, right? What do you think might happen with this? So I'm going to run So this has loaded, and I'm going to run this. So again, in the chat, people think, forget about the code or the subtleties, just by the logic of it potentially. This data set has the same group sizes, but less recaptures. What do you think might happen to things like the estimate and the detection probability of observer 1 and observer 2? You think it'll be more or less than this? Will it be the same? Yeah, Iftika, don't worry. I will. We can run through that. Like I'll check the GitHub once quickly. I'll put this on the GitHub. So what you see today, I'll put this one on the GitHub. So let's say there's nothing on the GitHub for now. But yeah. So yeah, I will just run this. Yeah, actually, sorry. Yeah. Do people have any guesses as to if for this output, will the estimate be similar to the first output? Will it be more or less? Will the detection probability be similar, more or less? So we have some answers in the chat. Ranjana says, okay, estimate should be same, detection will be less. Okay, interesting. Stefan said detection probably down, total up, and upper and lower limit more spread. Okay. Ariel says, oh, sorry, I lost you. Ariel says less captures will increase the estimate. Okay, interesting. Chloe says, I guess similar estimates but larger CI. Okay. Tashi says more recaptures, better precision. Okay, so then Tashi says for the first data set there should be better precision. Iftika says estimate will be lower. Okay. Danielle says less detection probability. Great. Okay. Lots of different answers and opinions. Great to get thinking. So let's have a look. I will quickly call this. So as you can see, I think Stefan, you were correct, if I'm not mistaken, and other people were correct in bits and pieces. With the second data, our estimate is a bit higher. So our first estimate was, if I just go quickly here, was about 171 blue sheep, whereas now it's about 200 blue sheep. And number of groups also increases, and I'll explain why. Group size stays the same, and that makes sense, right? Because we haven't changed the group size, so the whole the whole calculation for group size stays the same. Lower bound is about 157, so similar, but upper bound becomes much higher. So yes, there are wider confidence intervals, and as you can see, detection probability, which I think most of you said, is lower. For both observers, it's similar for both observers because in this case, we just have 11 groups and both observers, have unique number of observations which are similar, 3 and 3, which is why their detection probabilities become similar. The reason why it becomes bigger, and if you think about it logically, is in the second case with less recaptures, essentially what's happening is observers are missing more groups, right? And because they're missing more groups, it's likely the data that you have as the minimal input is much lesser than the actual estimate. In other words, for the first example, your minimum count is very close to the estimate, and hence, you have 171 because you're recapturing more, right? In other words, if you recaptured all groups, if there was 50 groups and you recaptured all, your minimum count and estimate will be very, very similar, if not the same. And that's not the case in the second example. Anyways, this is all for me from the code, and I hope this sort of clarifies the output. So I'm just going to go back, and I will share this code as I said in a bit. So feel free to run it. Obviously, don't change. What I would advise is don't change any of this. This part will not be changed at all, because if you obviously change it, the outputs will differ. But obviously, you can mess around with the models you want to use, and if you want to change the priors and all that. So yes, I will just go back to my presentation. Give me a second. So okay, there's some questions. Quick question. Yes, Tashi. Since this is Bayesian, shouldn't be credible intervals? Yes, exactly. Yes, Tashi, you're correct. Stefan has a question as well. Sorry. seamless group because some moved away because of observer one. Well, exactly, Stefan. So that's my point. If you think that's definitely true, which in my opinion, honestly, is not always the case. In majority of the cases, it might be, but it's not always the case. But if you do think that that is the case, you shouldn't use MT model. You probably want to be using the MB model and tell R that I think observer 2 suffered in his or her detection probability or their detection probability if it's a team because of observer 1. So you're not necessarily handicapped by that. Cool. And yes, Tashi, I think I answered your question as well. So yes, they are credible intervals. So moving forward, I will just, so this is what we, yes. So I'm just going to start a poll, guys. And it's going to be around these, this aspect is, itself. So let me just launch the poll. The poll is called, just understanding W observer data. It has 5 questions.